We present OmniTact, a multi-directional high-resolution touch sensor. In object manipulation settings, a robot needs precise information about the contact state between its end effector and any objects it is handling. Compared to the global view provided by 3D sensors and cameras, tactile sensing provides direct information about the exact forces the robot is exerting on the objects, making it useful for precise manipulation tasks. However, building a tactile sensor that can be used in a wide range of settings remains challenging. The sensor must be compact enough to interact with a variety of environments while providing the maximum possible resolution. A robotic finger must also be sensorized on as much of its curved surface as possible to provide rich information about contacts, regardless of what location and at what angle they occur, much like a human finger. In this work, we present a novel design for a tactile sensor, which combines the benefits of multi-directional sensing on strongly curved surfaces with high-resolution outputs. There are a wide variety of prior sensor designs that aim at combining compact dimensions with the ability of high-resolution sensing on strongly curved surfaces. The BioTact sensor has roughly the same size as a human finger and allows for multi-directional touch sensing. However, its resolution with a few dozen electrodes is much lower than that of optical touch sensors. Our sensor builds on the GelSight design, which consists of a camera that captures deformations on a gel slab. A key advantage of GelSight sensors over other tactile sensors is that the images provide a rich signal from which a wide range of relevant information such as object geometry, grasp stability, and object hardness can be extracted. The images from the camera can easily be used with standard convolutional neural networks, which have been tremendously successful in computer vision. Previous GelSight designs are relatively bulky and are sensitive on only one flat surface, which makes them difficult to use for some applications. Recently, a team at Columbia University introduced a sensor design that is applicable to strongly curved surfaces. Its sensing principle works similarly to a GelSight sensor, but instead of using cameras, it uses a combination of LEDs and photoresistors. While being potentially cheaper, it is challenging to achieve a similar resolution as GelSight sensors using this type of sensing. Our sensor design is driven by three main goals. First, our sensor is multi-directional, meaning that it has sensitivity on multiple sides of its curved surface. This enables the sensor to work in many different types of object manipulation settings. For example, sensitivity on one side of the sensor can provide information about an object grasp, while readings from the top can inform the robot about the location of obstacles in the environment. OmniTact satisfies this goal by providing 360 degrees of sensitivity in the horizontal plane and 270 degrees of sensitivity in the vertical plane. Next, the sensor should provide high-resolution signals from which we can extract features which are valuable for control. Optical tactile sensors such as GelSight are able to capture detailed spatial information, which is difficult for capacitive or resistive sensors. OmniTact uses 5 400 by 400 pixel micro cameras to provide high-resolution signals. Finally, a thumb-like form factor allows the sensor to fit into robot fingertips. The size of a tactile sensor can significantly limit the types of tasks that it can be used to perform. For example, a bulky tactile sensor may not be able to pick up small objects like a fork. We designed OmniTact with a 30 mm diameter and a 35 mm height. The GelSight sensor has four main components. The first is the camera, typically a standard high-resolution webcam. The camera captures images of deformations on the second component, the gel slab. Between the camera and the gel slab is an air gap. The outside of this gel slab is coated with a reflective aluminum powder, and the inside surface of the gel is illuminated by a red, blue, and green LED. OmniTact, on the other hand, uses multiple cameras and LEDs to capture deformations on its surface. It uses a similar gel encoding to the GelSight, except the gel is casted directly on the cameras to decrease sensor size. Here we can see examples of deformed sensor skin when pressed against common objects. We additionally show the readings from different views of the sensor as its contact angle against the gear rack is changed. Note that the impression is first visible in the view of the side-facing camera and as the sensor is rotated, eventually appears through the camera facing the tip of the sensor. To accomplish our goals of high resolution and compactness, we used microcameras typically used in medical endoscopy with field of views of 90 degrees. The 5 microcameras are arranged in a camera mount which has gel casted around it. As shown by the camera views, OmniTact has sensitivity similar to a human finger. In the vertical plane shown by the side view, the sensor has 270 degrees of sensitivity, shown by alpha. On the horizontal plane, shown on the right from the top view, the sensor accomplishes 360 degrees of sensitivity with minor blind spots. The total diameter of the sensor depicted by D is 30 mm, and the height of the sensor is 35 mm. The specific microcameras we use from the Shenzhen Eastern International Company are 1.35 mm by 1.35 mm by 5 mm long. Shown in the section views from our CAD below, we integrated 5 cameras, 1 top-facing and 4 side-facing, into our 3D printed camera mount by inserting them through channels. Camera cables are also routed out of the sensor through these channels. Similar to previous GelSight sensors, we arranged LEDs to illuminate the inner surface of the gel skin. To ensure even illumination, on OmniTact's camera mount in CAD, we arranged blue, red, and green LEDs equidistant from each microcamera. This surface was unrolled and manufactured into a custom-designed flexible printed circuit board. During assembly, the PCB is wrapped and glued around the camera mount as shown. We evaluate the use of our sensor for control on a task in which the robot must pick up and insert an electrical connector into a wall outlet using solely tactile feedback. This is challenging because the way in which the electrical connector is initially placed into the gripper varies, and therefore it requires the robot to both precisely localize how the electrical connector is positioned relative to the end effector as well as to the wall outlet. We mount the OmniTact sensor as 1/2 of a gripper mechanism on a modified 3-axis CNC machine, which provides precise control of the end effector position. To complete the task, the end effector first touches on the arena floor and takes a reading from the tip camera. It then closes the gripper around the textured electrical connector, getting information from the side camera. Then, based on the sensor readings, the optimal action for inserting the connector into the outlet is predicted and executed. We train a neural network model which takes as input the 2 tactile readings as shown in the image and directly outputs the desired end effector position target for a successful insertion. The model is trained on 100 demonstrations of insertions of the electrical connector, provided by commanding the robot's motions via manual keyboard control. Here we can see an example of a successful trial of the electrical connector insertion. The electrical connector is initially placed at one of several possible initial locations, and the neural network policy determines how to adjust the robot position to insert the plug correctly. We compare the performance of OmniTact on this task with policies which only use one of the camera views available to it, as well as a commercial optoforce sensor. We can see that the policies learned with both camera views significantly outperform policies using only the side or top cameras. Using both camera views allows the robot to succeed at both localizing the electrical connector and the end effector. Because of the high-resolution sensing of OmniTact, it is able to outperform the optoforce sensor by detecting the textured cues which are critical to localization. To summarize, we have shown that 1. Compact multi-directional tactile sensing can be achieved with multiple microcameras. 2. Multi-directional tactile sensing enables higher success rates for challenging tasks, such as inserting electrical connectors. And finally, tactile sensors like OmniTact could be the key for better robotic manipulation and teleoperation in various settings. Our paper link and code are available at the following website link. Please also join our Slack channel at the ICRA 2020 conference for any questions. Thank you.